Neutron stars are among the most extreme objects the universe has ever created, second only to black holes themselves. They are the collapsed cores left behind after massive stars explode as supernovae, the remnants of titanic deaths that tear apart stellar systems. What remains after such an explosion is a sphere no larger than a city, yet containing more mass than our entire Sunday. These are places where matter is pushed far beyond anything we can replicate on Earth. Atoms no longer exist as atoms. Electrons are forced into protons, forming seas of pure neutrons. Every teaspoon of this material would weigh as much as a mountain. To understand a neutron star is to step into physics on the edge of reality. Gravity here is so strong that even light bends sharply around the surface. Time itself flows differently. The magnetic fields can be hundreds of millions of times stronger than anything humans could ever create. These stars spin with breathtaking speed, sometimes hundreds of times per second, turning into cosmic lighthouses known as pulsars, sending beams of radiation sweeping across space. Neutron stars represent the densest form of matter in the universe that we can directly observe. They are, in a sense, atomic nuclei scaled up to the size of a city, cosmic objects made of pure nuclear matter. And inside them lies a frontier where our understanding of physics falters. The behavior of superfluids, quark matter, and ultra-dense cores that may hide phases of matter we have never seen. This video will explore what neutron stars truly are, not science fiction, not metaphor, but the real physics of what happens when nature crushes matter to its absolute limits. These are stars that died but refused to disappear, leaving behind some of the strangest, most mysterious objects in the cosmos. The birth of a neutron star begins with the death of a giant. When a massive star reaches the end of its nuclear life, its core, once supported by the pressure of fusion, starts to collapse under its own gravity. For millions of years, the star fought a delicate battle, balancing the outward push of radiation against the inward pull of gravity. But when the fuel runs out, gravity wins instantly. In the collapsing core, matter is crushed so violently that even atoms themselves fall apart. Electrons are squeezed into protons, merging to form neutrons in a process called neutronization. In a fraction of a second, the familiar structure of matter disappears, replaced by a sea of pure nuclear density. The collapse is so intense that the entire transformation happens in mere milliseconds, the time it takes for the core to shrink from thousands of kilometers across to a sphere no larger than a city. As this happens, temperatures soar to over 100 billion Kelvin, hotter than the center of any star that has ever lived. The outer layers of the dying star crash inward, rebound violently off the newly formed neutron core, and explode outward as a supernova. For a brief moment, the star outshines entire galaxies. And buried at the heart of this cosmic detonation is the newborn neutron star, a tiny, ultra-dense ember left behind after one of the most extreme events in the universe. This birth is unlike anything else in nature. It is not a gentle formation, but a catastrophic rebirth forged in pressure and fire. A neutron star is born in a flash of collapse, fusion of particles, shock waves, and unimaginable heat. In just a heartbeat of cosmic time, gravity compresses the core into the densest observable state of matter in the universe. The result is an object made not of atoms, but of pure neutrons, a remnant so extreme that even physics struggles to describe it. No other event in the cosmos creates something so small, so massive, and so violently transformed in such a short span of time. Unlike a black hole, which has no physical surface at all, a neutron star possesses a hard, solid crust, a place where the laws of matter reach their ultimate limit. This crust, only a few kilometers thick, is one of the most extraordinary structures in the universe. It forms as the blazing hot newborn neutron star cools, allowing the outermost layers to solidify into something unlike any material found on Earth. Here, atomic nuclei are packed so tightly that they merge into an exotic crystal lattice enriched with neutrons. Electrons drift freely like a sea of charged particles, and the density increases dramatically with depth. The further one descends into the crust, the less familiar matter becomes. This solid layer is believed to be the strongest material known to physics, up to 10 billion times stronger than steel. Under pressures billions of times greater than anything on our planet, the crystalline structure does not simply compress, it achieves a rigidity that defies intuition. A mountain on a neutron star may be no taller than a few centimeters, yet it can weigh as much as Mount Everest. Every centimeter of this crust stores monumental amounts of stress. And when that stress breaks, the result is catastrophic. Cracks in the crust cause what astronomers call starquakes, the neutron star equivalent of earthquakes. But unlike terrestrial quakes, these fractures send ripples through the star's magnetic field and rotational momentum. In milliseconds, the star's spin rate can jump abruptly, a phenomenon known as a glitch. These glitches are powerful enough to slightly alter the timing of pulsars, producing detectable changes in the signals that reach Earth even across thousands of light years. Each tiny fracture becomes a cosmic announcement that something has shifted deep inside one of the densest objects in existence. The surface of a neutron star is therefore not a calm, frozen shell. It is a tense, highly stressed boundary between normal matter and the ultra-dense nuclear interior. It is a skin stretched to its limits, capable of storing unimaginable force, cracking violently, and releasing bursts of energy that echo across the galaxy. In its solidity lies a paradox. The crust is rigid and crystalline, yet floats on top of a fluid ocean of neutrons beneath. Standing on such a surface, if that were possible, would be like standing on the outer layer of an atomic nucleus magnified to planetary scale. It is one of the most extreme frontos in all of astrophysics. Beneath the rigid crust of a neutron star lies a region so extreme that the very concept of an atom ceases to exist. This layer, often called the neutron soup, is a transition zone between the crystalline outer shell and the even stranger superfluid core. Here, matter is crushed to densities millions of times greater than in the core of any normal star. Under such conditions, the familiar structure of atoms, nuclei surrounded by orbiting electrons, cannot survive. Gravity squeezes everything so tightly that electrons are driven directly into protons, merging them into neutrons in a relentless process of particle fusion. This zone is composed of free neutrons, scattered protons, and a thin haze of remaining electrons, all suspended in an exotic fluid that behaves like nothing on Earth. There is no empty space between particles. Instead, they exist in constant quantum interactions, forming a dense nuclear liquid. Atomic nuclei that do exist are grotesquely distorted by pressure, stretched into unusual shapes that resemble long rods or sheets rather than spheres, a bizarre phase of matter scientists call nuclear pasta. Even these strange forms eventually dissolve as one descends deeper, leaving only the neutron-rich ocean beneath. The reason atoms collapse here is simple but profound. The density is so high that electrons no longer have room to maintain quantum orbitals. Their wave functions overlap, and the Pauli exclusion principle, the rule that no two identical particles can occupy the same quantum state, forces them into higher and higher energy levels until merging with protons becomes the only possible outcome. What remains is an unbound mix of neutrons and a sprinkling of protons, forming a fluid that is closer to the interior of an atomic nucleus than to any physical substance we know. This nuclear soup is not just dense, it is dynamic. Neutrons behave collectively rather than individually, moving through the star with properties of a quantum liquid that defies classical intuition. Vibrations in this layer can propagate with astonishing speed, and even slight disturbances can ripple downward into the core or upward into the crust, causing measurable effects such as pulsar glitches or bursts of radiation. To exist in this region would be to stand inside matter stripped to its rawest essence, where the architecture of atoms has collapsed and the particles that once built the universe's chemistry float freely in a supercompressed sea. It is a place where physics nears its breaking point, where matter is too dense to hold its shape, too energetic to remain stable, and too extreme to resemble anything that could exist under normal cosmic conditions. Deeper inside the neutron star, beyond the crust and the turbulent layer of nuclear soup, lies one of the most extraordinary states of matter in the universe, a vast ocean of superfluid neutrons. Here, the density becomes so extreme and the quantum conditions so compressed that neutrons stop behaving like individual particles and begin to act as a single, coherent quantum entity. This entire region, stretching for kilometers toward the core, is essentially one gigantic superfluid. Superfluidity is a state where matter flows without friction, without resistance, without losing energy. On Earth, the closest analog is liquid helium-4 cooled to just a few degrees above absolute zero. In that delicate laboratory setting, helium climbs the walls of its container, slips through impossibly tiny gaps, and moves as if gravity barely applies. But inside a neutron star, superfluidity is pushed to an unfathomably extreme limit. Temperatures here are still around hundreds of millions of degrees, but due to the crushing density and unique quantum balance, the neutrons behave as if they are frozen into perfect order, yet move with total freedom. This superfluid ocean is so smooth, so pure, that it can rotate only in discrete quantum vortices, microscopic whirlpools, each carrying a fixed amount of angular momentum. The entire neutron star's rotation depends on the arrangement of these vortices. When the star slows down due to electromagnetic radiation, the vortices must adjust. They shift, move, recombine. Sometimes they pin themselves to the crust above, storing rotational tension like invisible springs. And when they unpin all at once, the entire star experiences a sudden, measurable jump in rotation speed. These events are known as glitches, brief, sharp increases in a pulsar's spin rate. To an observer on Earth, they appear as tiny timing irregularities, but they represent seismic shifts in the internal quantum structure of the neutron star. A glitch is the moment when the superfluid interior rebalances itself, transferring angular momentum to the crust in a sudden burst. It is a reminder that this incredible quantum ocean, serene as it may seem, is constantly reshaping the star's internal dynamics. The existence of such a superfluid layer in a place of such violence is one of astrophysics' most beautiful paradoxes. The heart of a neutron star, born in the fury of a supernova, is governed by the quiet, perfect smoothness of quantum mechanics. It is frictionless, timeless, and utterly alien, a place where the classical world dissolves, and only the rules of the subatomic remain. To imagine this ocean is to imagine a star filled with liquid that can flow forever, rotate without slowing, and shift the heartbeat of the cosmos with the movement of microscopic vortices. Deeper within the neutron star, below the superfluid ocean of neutrons, lies another astonishing quantum domain, a region where protons become superconductors. Under immense pressure and extremely high density, protons pair up into Cooper pairs much like electrons do in terrestrial superconductors. But here, the environment is millions of times more extreme. What forms is not just a superconducting material, it is a superconducting star-sized core, a single region through which electric currents can flow with absolute perfection. Superconductivity means that magnetic fields cannot move freely inside the medium. Instead, they are forced into narrow, thread-like structures known as magnetic flux tubes. Each flux tube is incredibly thin, far thinner than a human hair by factors of trillions, yet carries an enormous magnetic field, locked in place by quantum mechanics. These tubes form vast lattices that thread through the star's interior like the strands of an invisible cosmic web. They define the shape, intensity, and stability of the magnetic field of the entire neutron star. In some neutron stars, the rarest and most extreme, these flux tubes help generate magnetic fields so colossal that they defy language. These objects are known as magnetars, with magnetic fields reaching up to 10 to the power of 1 Gauss, a million billion times stronger than Earth's magnetic field. If a magnetar were located halfway to the moon, it could erase the magnetic stripes on every credit card on Earth. Its field is so intense that it can distort the electron orbitals in atoms, alter chemical bonds, and even affect the vacuum of space itself. These magnetic structures are not silent. As the neutron star cools, shifts, and glitches, the superconducting layer strains against the crust above. The rigid crust tries to hold its shape, while the flux tubes anchored below pull and twist. This tension builds until the crust fractures, producing bursts of electromagnetic radiation that can be seen across galaxies. On magnetars, these events become giant flares, explosions so bright they can temporarily outshine the Milky Way. The superconducting interior therefore plays a central role in the star's surface activity. It is the unseen engine generating bursts, twisting magnetic fields, and driving the violent behavior visible on the surface. Every crust quake, every flare, every radio pulse from a magnetar is shaped by the ghostly lattice of flux tubes deep within, where quantum mechanics controls forces beyond anything the human mind can fully grasp. In this hidden world, superconductivity is not a scientific curiosity, it is the foundation of some of the most extreme events in the cosmos. Inside a neutron star, magnetism becomes architecture, tension becomes energy, and the quantum behavior of protons shapes the destiny of a dying star transformed into one of nature's most powerful engines. At the very heart of a neutron star lies one of the greatest mysteries in modern physics, a region so extreme that even the most advanced theories falter. The densities here exceed the density of an atomic nucleus by factors of several times. Under these unimaginable conditions, neutrons themselves may begin to dissolve. Their internal structure, the quarks bound tightly together by the strong nuclear force, may break apart, releasing a form of matter that has not existed freely since the first microseconds after the Big Bang. One possibility is the formation of a quark-gluon plasma, a state where quarks are no longer confined inside protons and neutrons but float freely in a dense, seething ocean threaded by gluons. This plasma would behave like a perfect fluid, with almost no viscosity, similar to what particle colliders briefly create in microscopic droplets, except here it could fill an entire star's core. If such a core exists, it means a neutron star is essentially a trapped piece of the early universe, preserved under unimaginable pressure. Another possibility is the emergence of hyperons, exotic particles that contain strange quarks instead of just the up and down quarks found in ordinary matter. Hyperons are unstable on Earth, decaying in fractions of a second, but deep inside a neutron star, the immense pressure may make them stable. Their appearance would soften the star's internal structure, transforming the equation of state and possibly controlling how massive a neutron star can grow before collapsing into a black hole. If hyperons exist in the core, they represent a completely new chapter of astrophysical chemistry, one where matter rearranges itself into states forbidden under normal cosmic conditions. The most speculative, yet tantalizing, idea is the existence of strange matter, composed of strange quarks bound in stable, ultra-dense configurations. If strange matter forms at the center, the star may not be a neutron star at all, but a strange star, an object built not from neutrons, but from chunks of stable quark matter. In theory, strange matter could be so stable that a droplet of it, if removed, would convert surrounding matter into more strange matter. Though this remains highly theoretical, its possibility makes the interiors of neutron stars some of the most feared and fascinating places in the cosmos. What truly lies inside these stars is one of the biggest open questions in physics. No laboratory on Earth can recreate such pressures or densities. Particle accelerators reach high energies, but never the crushing compactness of a neutron star core. That makes neutron stars natural laboratories for extreme high-energy physics, offering conditions impossible for humans to generate. A single measurement of a neutron star's mass, radius, or gravitational wave signature can reveal clues about quark behavior, particle interactions, and quantum forces that are otherwise forever out of reach. In a sense, the core of a neutron star is a time capsule from the dawn of the universe, a place where matter exists in forms older, stranger, and more fundamental than anything we can touch. Until we can decipher their interiors, neutron stars will remain cosmic riddles, stars that died, yet became windows into physics beyond our current imagination. The surface of a neutron star is one of the smoothest landscapes in the universe. Unlike planets or normal stars, where mountains can stretch for kilometers and valleys reach deep into the crust, a neutron star's gravity is so overwhelming that it flattens everything almost perfectly. Even the strongest known material, the neutron-rich crystalline crust, cannot withstand more than a tiny deviation from perfect symmetry. As a result, a mountain on a neutron star may rise only a fraction of a millimeter, perhaps a few millimeters at most. Some may be no taller than a grain of sand. Others may barely reach the thickness of a human hair. And yet, these tiny imperfections matter. In the gravitational environment of a neutron star, even a microscopic bump is enough to send ripples through space-time. Because neutron stars spin rapidly, many rotate dozens or even hundreds of times per second, any slight asymmetry in their shape becomes a powerful engine for gravitational wave emission. If a neutron star had no bumps, cracks, or mountains, its gravitational field would be perfectly symmetric, and rotation alone would not generate waves. But when the crust develops even a tiny irregularity, the rotating star begins to stir space-time itself, sending out rhythmic distortions that ripple through the cosmos at the speed of light. These stellar mountains therefore behave like cosmic tuning forks, producing persistent, nearly monochromatic gravitational waves. The waves are faint, far weaker than those produced by colliding black holes or merging neutron stars, but they are steady, continuous, and scientifically invaluable. Detecting them would reveal the size and structure of neutron star mountains, offering insights into the strength of the crust, the behavior of matter under extreme pressure, and the detailed dynamics of a spinning superfluid interior. This is why modern observatories such as LIGO, Virgo, and Kagra are actively searching for these signals. They scan the sky for the faint, steady hum of a single rotating neutron star shedding energy through gravitational radiation. Each candidate pulsar becomes a potential source, its frequency, spin rate, and position feeding into intricate signal processing algorithms designed to tease out ripples smaller than the width of a proton. So far, no continuous gravitational waves have been definitively detected, but the search continues, becoming more sensitive with every upgrade. Scientists believe that one day, as detectors become more refined, they will hear the whispers of these tiny stellar mountains. When that happens, humanity will finally be listening to the heartbeat of matter at its most extreme, encoded in the subtle trembling of space-time generated by bumps too small to see, but powerful enough to shake the fabric of the universe. Pulsars are among the most astonishing phenomena in the universe, neutron stars that rotate with such perfect regularity that they rival, and often surpass, the precision of atomic clocks. Their existence begins with the extraordinary magnetic fields and rapid rotation of a newly formed neutron star. As the star spins, its intense magnetic field funnels charged particles along its magnetic poles, creating narrow beams of radiation. These beams sweep across the sky like the beams of a lighthouse. If one of those beams happens to cross Earth, we detect a pulse, a sharp, rhythmic flash of radio waves, repeating with uncanny precision. The physics behind this cosmic lighthouse is breathtakingly elegant. The magnetic poles of the neutron star do not align with its rotation axis, so as the star spins, the beams trace circles in space. Each rotation sends a burst of electromagnetic radiation outward. For many pulsars, this pulse arrives at Earth with timing so precise that even after observing millions of rotations, the difference between predicted and measured pulses can be smaller than a microsecond. It is as if a dying star has become a celestial metronome, tapping out a steady rhythm across the galaxy. Different kinds of pulsars reveal different chapters of this story. Millisecond pulsars spin at extraordinary speeds, hundreds of rotations per second. Their rotation periods are so stable that they are used to test the most delicate predictions of Einstein's general relativity. These rapidly spinning pulsars often form in binary systems where a neutron star has been recycled, absorbing gas and angular momentum from a companion star until it spins like a quantum gyroscope. Binary pulsars provide even deeper insight into gravity. In these rare systems, two neutron stars orbit each other, sometimes both visible as pulsars. Their gravitational dance subtly alters the timing of their pulses, offering a window into the curvature of space-time and the emission of gravitational waves. Observations of binary pulsars gave the first indirect proof of gravitational waves long before detectors like LIGO were built. X-ray pulsars, on the other hand, are powered not by rotation alone, but by matter falling onto the neutron star from a companion. As gas spirals inward and crashes onto the magnetic poles, it heats up and emits intense X-rays. These pulsars blink not in radio wavelengths but as bright, energetic bursts in the X-ray sky, revealing the ferocious power of accretion onto a magnetic neutron star. Across all types, the pulsar phenomenon reflects the incredible diversity and precision of neutron star physics. These stars, forged in violent collapse, become some of the universe's most reliable timekeepers, cosmic lighthouses whose beams can cross thousands of light-years unchanged. With every pulse, they carry information about gravity, magnetism, rotation, and the deep structure of matter under conditions no laboratory can reproduce. They are the universe's way of speaking in rhythm, sending out signals from the brink of physical extremes. Binary neutron star systems represent some of the most dramatic relationships in the universe, two ultra-dense stellar remnants locked in a gravitational dance that can last billions of years. Each star is only about 20 kilometers wide, yet contains more mass than the Sun. When two such objects orbit each other, their gravitational attraction is so intense that space-time itself curves and vibrates between them. Over time, the system slowly loses energy in the form of gravitational waves. This causes the orbit to shrink, the stars to spiral closer, and the entire system to accelerate toward a catastrophic finale. As the stars approach their final moments, their velocities climb to a significant fraction of the speed of light. Their magnetic fields twist and collide, their surfaces distort, and tidal forces tear at each other's crusts. The final seconds are a violent ballet of extreme physics, space-time stretching, neutron-rich matter flowing between the stars, and gravitational waves ringing out with ever-increasing frequency. The crescendo arrives when the two neutron stars collide, an explosion not of light alone, but of nuclear matter itself. This collision, known as a neutron star merger, unleashes energies that rival the brightest explosions in the universe. The merged object momentarily becomes a swirling mass of nuclear density matter, too dense to remain stable, often collapsing into a black hole within seconds. Surrounding this collapse is a hot, turbulent disk of neutron-rich debris. From this disk, jets of ultra-relativistic particles may erupt, creating short gamma-ray bursts, some of the most powerful explosions ever observed. But the most profound outcome of these mergers is the creation of heavy elements. Gold, Platinum, uranium, elements that require enormous neutron fluxes to form, are forged in the violent aftermath of the collision. The debris expands outward in a glowing cloud known as a kilonova, where neutron-rich matter undergoes rapid fusion, the R process, to build the heaviest atoms in nature. Every piece of gold jewelry on Earth, every atom of platinum in electronics, likely traces its origin to an ancient neutron star merger somewhere in our galaxy. The significance of these collisions was confirmed spectacularly in 2017 with GW 170817, the first event ever detected in both gravitational waves and light. LIGO and Virgo recorded the gravitational signal of two neutron stars spiraling together, while telescopes across the world watched the sky flare with the glow of a kilonova. For the first time, humanity witnessed the full story, space-time rippling from the collision, followed by the birth of heavy elements. It was a moment that united gravitational physics, nuclear physics, and astrophysics into a single, breathtaking narrative. Binary neutron star mergers are therefore not just cosmic catastrophes. They are the engines that enrich the universe, seeding future planets and future life with the elements necessary for worlds to form. In their violent deaths, they sculpt the chemistry of the cosmos, leaving behind signatures of their existence in every atom heavier than iron. There exists a razor-thin boundary in the cosmos, a limit so fundamental that it decides the fate of dying stars. At one side of this boundary lies the realm of neutron stars, objects sustained by the quantum pressure of neutrons packed together in a density beyond imagination. On the other side lies the ultimate collapse, a black hole. The key that separates these two extremes is the Tolman-I-Oppenheimer-Avolkov limit, often called the TOV limit. It represents the maximum mass a neutron star can possess before its internal pressure is no longer sufficient to counteract gravity. A neutron star is supported by neutron degeneracy pressure and the strong nuclear force. These forces collectively push back against gravitational collapse with extraordinary strength. But even they have limits. As more mass accumulates, through accretion, mergers, or the star's own evolution, the core becomes more compressed, the neutrons pushed closer together, and the internal pressure rises to the edge of what physics can describe. If the mass surpasses the TOV limit, the neutrons can no longer resist. No known force in nature is strong enough to halt further collapse. The star's structure gives way, space-time caves inward, and the object slips across the event horizon, becoming a black hole. What happens during this transition is one of the greatest mysteries of modern astrophysics. The final milliseconds of a neutron star's life cannot yet be simulated with full precision. Does the star collapse smoothly? Does it undergo violent oscillations? Does exotic matter, quarks, hyperons, strange matter, briefly dominate the core before disappearing behind the event horizon? The answers remain hidden, locked within a region of physics where densities surpass anything achievable on Earth. The exact value of the TOV limit is also unknown. Most estimates suggest it lies somewhere between 2.0 and 2.5 solar masses, but observations occasionally hint at neutron stars that challenge this range. The uncertainty arises from the unknown equation of state of ultra-dense matter, the behavior of nuclear particles under pressures trillions of times greater than in atomic nuclei. Without this equation, we cannot predict the precise moment when a neutron star must collapse. Thus, the boundary between neutron stars and black holes remains blurred, a frontier of ignorance carved into the cosmos. Every newly discovered massive neutron star, every gravitational wave signal from a merger, brings us one step closer to mapping this threshold. In this way, the TOV limit becomes more than a number. It is a cosmic riddle, the line between two states of matter, and a challenge to our understanding of the universe. Neutron stars stand as the most extraordinary meeting point between quantum physics and astrophysics, a realm where the smallest laws of nature shape the largest structures in the universe. They are the final embers of once massive suns, yet inside them unfolds physics far more exotic than anything produced in laboratories. In their cores, matter exists in a state that defies intuition, atoms crushed beyond recognition, neutrons bound into quantum fluids, protons arranged into superconducting layers, perhaps even stranger particles lurking in the depths. These stars reveal how matter behaves under conditions that no experiment on Earth can replicate, pressures so immense that space itself bends, temperatures that rival the early universe, and densities that transform familiar particles into something alien. What makes neutron stars uniquely precious is that they are not abstractions or theoretical exercises. They are real objects, scattered across the Milky Way, rotating, glowing, and speaking to us through pulses, X-rays, and gravitational waves. They give us direct access to the behavior of ultradense matter, to the limits of nuclear forces, and to the threshold where quantum effects determine the fate of astrophysical giants. Each observation, a starquake, a pulsar glitch, a merger detected by LIGO, is a message from a world where the laws of physics are stretched to their breaking point. They remind us that the universe is not only vast but profoundly strange. For in the hearts of neutron stars lies a question as ancient as the cosmos itself. What can the universe create from a single atom when gravity becomes absolute? Here, at the frontier of collapse, matter is pushed into forms that challenge our understanding, offering a glimpse into the first moments after the Big Bang and perhaps into states of matter that existed only in the earliest flash of creation. These stars are cosmic laboratories, monuments to extreme physics, and silent vaults of mysteries we have only begun to uncover. And so the story ends with a quiet truth. Neutron stars are not merely remnants of death, but archives of the universe's deepest secrets. They hold within them the possibility that, even at the edge of destruction, nature continues to weave new and astonishing forms of existence. In the dim hearts of neutron stars lies the answer to the question, what can the universe make out of a single atom?